So welcome everybody to the second day of our workshop on optimization for AI. We have a pretty exciting lineup of talks today, and leading that is Professor Quanquan from Department of Computer Science at UCLA. John is an accomplished machine learning researcher, and we are very happy to have him here. So,
Thank you for inviting me. And so today I'm going to talk about something new, and it is built up on variance reduction. So the algorithm, we call it MARS. And the goal of this project is trying to unleash the power of variance reduction for training large language models. So for some of you in the audience or on the Zoom, I believe you have worked on variance reduction, and I have been working on variance reduction for quite a long time. And the most exciting thing about variance reduction is it can usually help us design algorithms that can achieve faster convergence. But the downside of variance reduction is when we apply it to training deep neural networks, it usually doesn't work. So this is like long-standing questions for people in the community of stochastic optimization. So if you look at so before I dive into the details of the algorithm, I want to give you a very a quick and brief overview of the history of large language models, because this is the model we want to optimize using variance reduction. So in 2017, transformers was invented by a group of people at Google. And since then, people built different language models from GPT to BERT to GPT-2 until, for example, GPT 3.5 or Instruct GPT in 2022. And then in November 2022, ChatGPT was launched by OpenAI, and it has gained a lot of attention. And the following March in the following year, GPT-4 was released, and the performance of GPT-4 and also the user experience of ChatGPT has been improved by a huge leap. And these days, people are talking about large language models, and there are more and more competitors joining this race game between OpenAI and, for example, Google, Meta, and many other high-tech companies. They all want to build their own large language models. And I think for people in academia, Llama is probably our favorite models. And then early this year, there's DeepSeek R1, which is a reasoning model created by DeepSeek, which is a company in China, and it has also received a lot of attention. Okay, so this is just a brief history of large language models. Of course, it is an incomplete list of large language models. And if you look at the optimizers people are using to train those large language models, actually the most widely used one are Adam and AdamW. So Adam is an optimizer proposed in 2015, and if you check news frequently, you probably see the paper of Adam has already received the Test of Time award for this year's iClear. So if you are going to iClear next week, you'll probably have a chance to attend the talk given by the authors of Adam. And in 2019, there is another paper called the decoupled weight decay. So the idea of the decoupled weight decay is you do not treat weight decay as like L2 norm regularization added to the object function. You just add the weight decay term when you calculate the gradient. Okay, and this will give you algorithm, they call it AdamW. And to my knowledge, AdamW is probably one of the most widely used optimizer people are using for training large language models. So everything looks great, but as an optimizer or as a researcher in the optimization community and the machine learning community, we all want to deliver better and faster optimizers. So since the popularity of like AdamW, people want to improve AdamW, and there are a lot of papers, at least hundreds of papers trying to do that. But to my knowledge, some of them can indeed improve AdamW, but only in certain scenarios. When you apply the optimizers to larger language models, usually AdamW is still the the most effective and efficient optimizer. And on the other hand, if you look at the optimization algorithms, especially adaptive gradient method and the variance reduction method in the literature, it has also evolved from very early algorithm called RPROP. Many of you probably haven't heard of it, but it's an algorithm implemented in PyTorch. It's a very relatively old algorithm, was invented in 1993. And I think the most famous one is AdamW, which was proposed in 2010, 15 years ago. And since then, there are a sequence of work trying to extend the idea of adaptive learning rates into different optimization algorithms, including Adam and AdamW. And on the other hand, if you look at the development of variance reduction algorithms, in the machine learning community, the first one is probably called SAG. Okay, it was proposed by Mark Schmidt, Franz Bach, and co-authors in 2013. And there's another algorithm called stochastic dual coordinate ascent, SDCA, it was also proposed around that time. So both of them, you can view them as variance reduction. But the most widely used variance reduction algorithm, I would say, is probably SVRG. It was proposed the year after, and the reason SVRG becomes so popular is it's very easy to implement, and it's memory efficient. Okay, so I will briefly introduce SVRG shortly, but if you keep tracking the development line of research, you will see later there are some new algorithms called Zara, Spider, SNVRG, Spider Boost, and then Storm. Okay, I believe there are more algorithms along this line, but
okay.
Yeah, so when I say it's a memory efficient, it's mainly compared with Saga, because in Saga you need to maintain a huge gradient table. It's like a D by N a matrix. But in SVRG, you don't need to maintain such a huge memory block to store the gradient of all the training data points. Yeah. And then it's very natural to think of the following question. Can we, for example, combine the idea of adaptive gradient descent and variance reduction? And this is indeed something people have already explored. In 2020, there's a paper called Adam Plus. It combines variance reduction with Adam. And then there's an algorithm called Super Adam in 2021. And later, there's an algorithm called Ada Spider. So I'm not going to go over every single algorithms which combine the idea of variance reduction and adaptive gradient method. But what I want to say is, unfortunately, for some of these algorithms, it may work on small-scale experiments. In other words, variance reduction can be useful in certain scenarios. But when you apply these algorithms to training neural networks or language models, none of them really works. So that's the challenge we want to tackle in this project. So the question we raise is, can we apply variance reduction to improve the performance of training large models? So here by large models, I mean large language models or very deep neural networks like ResNet, efficient transformer, and so on. And now here's the algorithm we proposed. Okay, so we proposed Mars. It's not 2025, it should be 2024 because we put this paper on arXiv last November. And so let me give you like an overview of what the algorithm Mars, what kind of features it has. So it's a unified framework. We try to unify different variance reduction algorithms, different adaptive gradient algorithms with variance reduction. And it can accommodate different kind of approximate or exact hashing choice, which will give you different like instantiations of Mars. For example, Mars AdamW or Mars Shampoo, which I will introduce in detail. And in terms of convergence rate, we can prove t to the power of minus 2/3 convergence rate to the first order stationary point compared to 1/square root of t convergence rate achieved by Adam or AdamW for non-convex optimization. And of course, we have done a lot of experiments to showcase the performance of Mars for training large models. All right, so this is a brief history, and I just want to give you a picture about the history of large language models as well as variance reduction and adaptive gradient method. So now I will switch the gear a little bit to go into the details of the algorithm design. So first of all, this is the setting of stochastic optimization. You want to minimize some function which is defined as an expectation of some like a random function indexed by some random variable cosine. And SGD, stochastic gradient descent, is of course the most natural algorithm to be used for stochastic optimization. And we know that if the function is a non-convex, and then SGD need 1/epsilon to the power of 4 stochastic gradient evaluations to find the epsilon approximate first order stationary point, which is a point where the norm of its gradient is bounded by epsilon. And the variance reduction is proposed to reduce the variance of a stochastic gradient estimator, and which can further improve the convergence rate, because this 1/epsilon to the power 4 convergence rate is or iteration complexity is considered not optimal. Okay, so in the literature of variance reduction, people propose different ideas to reduce the variance of the stochastic gradient estimator. So one of the stochastic gradient estimator proposed in the literature, in the paper of SVRG, is something like this. So you can see that xt is the iterator in the tth iteration, x tilde is the reference point. So you minus, you take the difference of these two stochastic gradient, and then you add the full gradient evaluated at x tilde. So it's very easy to verify that. First of all, MT is the unbiased estimator of the gradient evaluated at xt, because if you take expectation, the second term and the third term will be canceled out. And in addition, if you take the variance of MT, then you can show that the variance of MT can be bounded by the smoothness parameter L times the difference between xt and x tilde. So remember that when the optimization algorithm make progress, you will update this reference point periodically. Therefore, so xt and x tilde, they will get closer and closer during the optimization process. So in other words, the variance of MT will diminish when the algorithm make progress. So this is the idea of variance reduction, especially the idea of SVRG. And then Sarah or Spider algorithm were later proposed. Instead of introducing this reference point or anchor point, they do not need to periodically introduce this reference point. They just recursively update the momentum mt. So given the previous momentum mt minus 1, they will calculate the new momentum at time t by adding the difference of these two stochastic gradients. Okay. But one thing I want to mention is for both of these two stochastic gradients, the randomness are same. So both of them are indexed by psi t. Okay. And then you just take one step descent along the negative direction of the momentum mt. Okay. So this is the idea of a spider. And we can prove that if you apply Sarah or spider algorithms properly, then you can find the first order stationary point within 1 over epsilon cubic stochastic gradient iterations. So this improves the 1 over epsilon 4 to the power 4 iteration complexity achieved by SGD. And then later, people just found that because in Sarah and spider, you still need to periodically restart. And this makes the algorithm like a multi-loop algorithm. And in order to convert an algorithm from multi-loop algorithm to single-loop algorithm, here's the algorithm called a stochastic recursive momentum or storm. So the idea of storm is they introduce a multiplier beta 1 to the second term and the third term in the definition of this Sarah or spider estimator. And by some algebra manipulation, you can write the update rule for the momentum term in store as this exponential moving average, where beta 1 is the parameter for this exponential moving average. And the CT is defined in this way. And in particular, if you look at the definition of CT, the first term is the stochastic gradient. And the second term is some scaled version of gradient correction, which is the difference of two stochastic gradient iterated at two consecutive iterates, but share the same randomness. And the storm can achieve the same iteration complexity as spider. Okay. But unfortunately, if you apply spider or storm to training neural networks, none of these algorithms work. Now, here comes the core idea of our algorithm. So we propose to introduce a scaling parameter gamma t in front of this gradient correction. Okay, so if you look at the gradient correction in storm, it's just multiplied by beta 1 divided by 1 minus beta 1. Beta 1 is the parameter for exponential moving average. And we introduce this additional scaling factor gamma t. And the gamma t can depend on time t. And in practice, you can also choose gamma t as a constant, which is independent of the iteration t. And why introducing gamma t is reasonable? So let's look at the two extreme case. If gamma t equal to 0, then you can see that it will reduce to just the exponential moving average. And the EMA actually has also been widely used in training, for example, diffusion models and many other scenarios. And if you choose gamma t equal to 1, it will reduce to the storm estimator. Now, more rigorously, you may ask why introduce gamma t can improve convergence. Okay, so here's the answer. So let's first look at why introduce gamma t in the SVRG estimator can improve the convergence. Because if you consider the SVRG gradient estimator, it's essentially like x minus gamma times y minus the expectation of y. So here, gamma is multiplied to the difference between y and the expectation of y. And you can, this is a function, quadratic function of gamma. Therefore, you can find the optimal gamma by optimizing this function with respect to gamma. And if you plug in the optimal gamma actually can be computed as this one. So in the numerator is the covariance between x and y, and in the denominator is the variance of y. And if you plug in this gamma, the optimal gamma, back into the above equation, you will see the variance of this estimator will be strictly small than the variance of X. So in other words, if you do variance reduction by this control variate, then you will achieve smaller variance than without doing variance reduction. But the case for storm actually is much more complicated because if you go into the details of the algorithm and the analysis, you will see that there are three random variables X, Y, Z, and the multiply gamma actually only appears in front of Y instead of the difference between Y and the expectation of Y. And due to this difference, actually this is a huge difference, then the analysis will be quite different, okay? But before we optimize this estimator with respect to gamma, so let's take a look at two special cases. So when gamma equal to 1, the above estimator will be upbounded by the second order momentum of Z plus 2 times the variance of X and 2 times the variance of Y. And when gamma equal to 0, it will reduce to this one, okay, which can be significantly larger than choosing gamma equal to 1, okay, if Z is the dominating term. So in other words, it's reasonable to imagine that between 0 and 1, there should exist the optimal gamma that will give you the smallest variance, the estimator with the smallest variance, okay. And indeed, if we do some calculation, we can show that the optimal choice of gamma will be given by this formula. Okay, so due to time limit, I'm not going to show the calculation process, but the key message from this slide is there exists the optimal gamma star. And that's the reason we want to tune gamma instead of choosing gamma equal to 1. Okay. And now here's the algorithm we propose. You can see that the key feature of this algorithm is when you calculate CT, we introduce a tunable parameter gamma t. And then we do projection. If CT is outside of the unit ball, we will project the CT back into the ball. Okay. And then we update the momentum MT using exponential moving average. And then finally, we solve like a preconditioned optimization, just one step preconditioned gradient descent. And in the following slides, I will show you when we choose this HT in different ways, then we can give different instantiations of mass. The first instantiation of mass is mass AdamW. If we choose HT in this way, then we can convert this update rule to be the same as AdamW. Okay, so in other words, we can apply the idea of scaled variance reduction to AdamW, and the resulting algorithm, we call it mass AdamW. And this is the algorithm. And the second example is line algorithm. Line is actually just the stochastic sign gradient with momentum. And if we choose HT in this way, we plug in this HT into the master algorithm of mass, then we will get a mass line, which is illustrated here. Okay, so the key is we use the sign of the momentum rather than the normalized. So in other words, we are using this L1 norm to normalize, coordinate-wise, absolute value to normalize the momentum. And the last example is a Shampoo. Okay, so Shampoo is a very famous algorithm proposed by a group of people in Google. The idea is instead of factorize the gradient, because when you train a neural network, for many parameters, they are 2D parameters. They are essentially matrices rather than vectors. If you do standard like a vector-based optimization, you need to convert those matrices into vectors. However, you don't have to do that, because by doing that, you will get very huge Hessian or second order momentum matrix. Therefore, you can directly play with the 2D matrix. And then you can do normalization by introducing the left matrix and the right matrix, and then do normalization properly. And if you choose HT in this way, then we can instantiate Mars to be the Shampoo version. And another nice thing about the Shampoo is if you, for example, do S3D of GT, then you can show that this gradient update can be simplified as this one, where UT and VT are the left and the right singular matrix of GT. And this is actually essentially the sign of the matrix, because for a scalar or a vector, we know how to compute the sign, right? A scalar is just if it's greater than 0 is equal to 1, less than 0 equal to -1. But for matrix, what's the corresponding notion of the matrix sign? The matrix sign actually is essentially just the UT times VT transpose, where UT and VT are the left and right singular matrix of the matrix. Okay. And this is resulting Mars Shampoo algorithm. And another thing I want to mention is in variance reduction, we need the randomness at 2 consecutive iterations to be the same. So in other words, we need cosine t here and also cosine t here. But in practice, we want to save memory and also save computation. So we will just replace this cosine t by cosine t minus 1. So in other words, we will use the stochastic gradient from previous iteration to approximate the stochastic gradient in the current iteration for the older iterate. And this will give the approximate version of Mars. And by some experiments, we show that if we are using approximate version of Mars, it will only sacrifice the performance a little bit. So this green line is the approximate version, and the right line is exact version. So they are very close to each other. And another algorithm, probably some of you in this room have heard of that. It's called a mu. This algorithm is proposed by Keller Jordan. He's now a researcher at OpenAI. But when he proposed this algorithm last year, I think it has received a lot of attention on social media. So what is this mu algorithm? And by some, so this is the algorithm of mu. I'm not going to going over each step of the algorithm. But what I want to highlight is by certain like algebra manipulation, we can show that mu actually is just a scaled version of Mars Shampoo with the approximate gradient. Okay, so this is their algorithm, and by several steps of algebra manipulation, we can obtain this one. And this one is just a scaled version of Mars with approximate stochastic gradient. And we can also show that Nestraff's acceleration is a special case of Mars. So this is Nestraff's acceleration. So remember that there are several versions of Nestraff accelerated gradient descent. So this is just one proposed in 1983. And by some change of variables and some algebra manipulation, we can derive the momentum update for Nestraff acceleration in this way. And then you can see that Nestraff acceleration is a special case of a Mars approximate when you choose the scaling parameter in Mars to be 1 minus beta 1, and choose the learning rate eta t to be eta divided by 1 minus beta 1. So remember that this beta is the momentum parameter in Nestraff's AGT.
All of these algorithms that you described in some way, just like a 2-parameter version of this acceleration, which is different versions of parameters.
I think one of the reasons why we can absorb so many existing algorithms as a special case is the storm estimator. The storm momentum is general enough to, and if you introduce a scaling parameter in front of the storm momentum, then we will be able to unify many existing algorithms.
It's basically just different choices of the parameters, right?
Yeah, different choices of the scaling parameter gamma. And we also show that 0 or 1 is not optimal for gamma. There should exist some like gamma in between 0 and 1, which will give you the smallest possible variance for the scaled storm estimator. Yeah. All right. So due to time limit, I will try to go over the theoretical result quickly, okay? And then I will show you more experimental results. So in order to analyze the mass algorithm, we need to make, you have a question? Yeah.
Yeah.
Mm. Yeah. So you can see that this is essentially like normalizing the spatial, because the singular value, the maximum singular value of UT times VT transpose equal to 1. Yeah, so you are essentially like normalizing the 2D gradient such that the maximum like magnitude will equal to 1 in the eigenspace. Yeah. Oh, by the way, this is not our like contribution. This is the observation I think used in mu algorithm, and there are another paper I think also carefully discussed this connection between mu and this normalized like this matrix sign. Yeah. All right. So in order to do the theoretical analysis, we make two assumptions. One is a bounded variance. This is a standard assumption when we do the analysis in stochastic optimization. The second one is L smoothness. So we assume each function is L smooth. It is called individual L smooth. And we also need to assume the Hessian is positive, but this is actually not an assumption, because if you look at the implementation of all the existing adaptive gradient method, you need to introduce some like a truncation parameters to make sure the second order momentum is strictly positive. So we assume there's a lower bound on the smallest eigenvalue of the Hessian estimator, which is lower bounded by rho. And this is the convergence rate. It looks a little bit messy, but I can walk you through it a little bit. So the left-hand side are two like quantities, and why we care about these two quantities, I will explain it later. But on the right-hand side, you can see that the first term is in the order of log t divided by t to the power of 2 divided by 3, and that's the reason we can achieve 1 over epsilon cubic iteration complexity. And the second term, which is highlighted in red color, actually is a negative term, is a minus term. And why we can get this minus term? Because we introduce this scaling factor gamma. And gamma actually will appear in the definition of MT, which I'm not showing on the slide. And you can see that this algorithm, this result is very interesting, because we can get this negative term show up on the upper bound of the convergence rate. And this negative term is the reason why our algorithm can potentially achieve faster convergence rate. And now I will explain why we care about these two quantities. Because first of all, these two quantities are both the norm square, right? So if we introduce like the Lyapunov function, which is the summation of this quantity without square, and this quantity without a square, then we can, by triangle inequality, Jensen inequality, and some other like manipulation, we can show that the gradient norm square at xt can be upbounded by some like a summation of the right-hand side, and that will give us the 1 over like log t over t to the power of 1 over 3 convergence rate. And this can be translated to 1 over epsilon cubic iteration complexity. And for mass AdamW, this special algorithm, we have the weight decay. So there's an additional term in the convergence rate, which depend on lambda. Due to time limit, I'm not going to explain it in further detail, but it will just have some additional term, which is highlighted in this blue color. And the lambda is just the weight decay parameter. Okay, now I will show you quite a few experiments. So this is the training curve of mass, as well as many other baseline algorithms for a GB2 large size model. So this model has 770 million parameters. And you can see that mass AdamW or mass line, these two instantiations always gives you the top two the best two performance. And these are the performance evaluation on some benchmarks. And you can see that the model trained by Mars AdamW or Mars line can usually gives the best downstream evaluation performance. So these bolded numbers are the best, the highest number in each column. And we've also applied Mars to traditional computer vision or image classification tasks. And you can see that Mars or Mars Shampoo or Mars line, they consistently gives you the best performance in terms of test loss, the lower the better, or in terms of the test accuracy, the higher the better. And this is the numbers. And we've also done some ablation studies about the tuning, this scaling parameter gamma. Remember, this gamma is very important in our algorithm. So we tried a different value of gamma from 0.0001, which is very close to 0, to 0.2. Because if we choose larger gamma, the algorithm will not perform very well. So we just carefully searched the value of gamma between this range, within this range. And our findings are, if we choose gamma to be 0.025 or 0.05, okay, it will get the best performance for Mars. And this is the suggested parameter choice for this gamma in our algorithm. And we also tried a constant learning rate schedule, because these days when you train neural network, you train large language models, you often start with warm up, which is like a linear increase in the learning rate. And then you stabilize the learning rate, so constant learning rate. And then you are doing decay. So if we consider constant learning rate schedule, you can see that the Mars algorithm with different choice of learning rate are consistently better than the corresponding AdamW algorithm. So everything are aligned except the algorithm are different. The learning rate are chosen to be the same. We also test our algorithm with the so-called warm-up, stable, and decay WSD learning rate schedule. And you can see that Mars also gives you the best performance. And this spike is because when you do this decay, the learning rate will, the training loss will, or validation loss will just decrease very quickly. And this is also very common if you're babysitting the training of large language models. Okay, so takeaway. We introduced this Mars algorithm. Actually, it's a unified algorithm framework. The motivation is we want to make variance reduction work for training large models. And the key idea is we introduced the scaling parameter, gamma. And I already explained why we needed this gamma. And it turns out to be very essential and also very effective in order to make variance reduction work for training large models. And the nice thing about Mars is you can just unify, or you can incorporate variance reduction into many existing algorithms like AdamW line or Shampoo, and the resulting performance will be consistent better than the corresponding algorithms. So here are the authors of this paper. And if you want to try this algorithm by yourself, you can also just download the code from this GitHub repo. All right, so that's all. Thank you for listening.
Questions for the one?
Mm-hmm. Mm-hmm. Yeah, that's a great question. And actually, this question is not specific to optimizer. If you look at, for example, the Llama or other like large language models, there are like a KQV projection matrix. There is like a projection, like a down and the down projection and up projection in the FFN. So all these parameters are 2D parameters. So only the word token embedding and the language model height, there's some like a vector valued parameter, but the remaining parameters are all matrix or 2D parameters. So when you choose a learning rate, actually it's better to choose a learning rate, different learning rate for different layers. And this is something I think is important in practice. And when we talk about math, actually we do not consider using different learning rate for different layers of the neural network. But in practice, you need to be very like cautious when you if you are using the same learning rate for different types of layers, you may not get the best possible performance. But why we want variance reduction? Because when we train those large language models, although the batch size can be chosen to be very large, but we still observe very like a huge variance. And sometimes there's a spike in the loss. And by using a variance reduction, we hope we can reduce the variance of the gradient, stochastic gradient estimator, even though there are still some intrinsic variance caused by the data. Because the portion of the training data can be very different, and you will do different like data scheduling. For example, you first train the model using intermediate or median level quality data. But when you do like annealing, in other words, when you do decay, you want to feed into many like high quality data, and the high quality data are usually like a code data or mass data. But for those median level quality data, it could be like any data you crawled from the internet, and you do data cleaning to make sure there's no like duplicate data, or there are no like data with incorrect formats. So it's a very complicated engineering problem. Yeah, but the idea of using variance reduction is just to make sure we can given the same data set, we want some algorithms that can control the variance of the gradient estimator so that the training will be more stabilized and therefore will converge faster. Oh, there's one more.
Quick.
Oh.
Okay, go ahead.
I'm just wondering if you think your research disproves the generalization theory for neural networks.
Disprove the generalization of neural network. What?
Reconciliation hypothesis. Like, I feel like a couple of the methods talked over the past few days are kind of like showing that's super wrong.
The run.
What?
You are talking about the run, or
Yeah.
or minimizing the run of the.
No, maybe we can talk later.
Question.
Yeah.
Okay, so just to make this, let's thank.
Yeah. Thank you.